In section 3.1, we learned some shortcuts to taking derivatives, and we'll go through why you can take these shortcuts here. So if f and g are differentiable functions and c is a constant number, like, I don't know, 3, and n is a real number, so pick your favorite real number, the derivative of a constant, all right, remember what the derivative means. It's what's the slope of a tangent line at some constant function y equals c. Well, again, if you think about the slope of y equals c anywhere on that graph, so let's say just c is 3, the slope of a horizontal line is always going to be 0, regardless of what point on that line. That tangent line is going to have a slope of 0. So the derivative of a constant is always 0. The derivative of x, or d dx, or sometimes I'll put the prime after the x. What is the slope of a tangent line on the line y equals x? Well, again, if we think of the line y equals x, that's that line. So up 1, or over 1, up 1, over 2, up 2, and so on. Well, this line has a slope constant of 1. So the derivative of x is just 1. With that, along with these next few rules, we're going to be able to take the derivative of like polynomials. And we've done this before, only we did it with limit. Like, what's the limit of a constant? It's always 0. So sum and difference rules, I can take the sum or the difference of the derivatives and break it up. So this would be the same as d dx of f of x. So I can take the derivative of f of x plus or minus the derivative of g of x. All right. Constant multiple rule, I can pull the constant out in front of the derivative and then just take the derivative of d dx of the function. All right, so we can do this sort of distributive with the derivative if there's addition and subtraction, but you can't distribute derivatives over multiplication and division. And we're going to see in section 3.2, we have the product rule and the quotient rule for derivatives. But we can't, so you cannot take the derivative of f of x times g of x and say that it's the derivative of f times the derivative of g. And we'll see why, like I said, in the next section. But we have a specific rule that allows us to take derivatives of products and quotients. So an example of the above rules, and we're going to again see that there's a way to shorten this, the derivative of, for example, 3x plus 7. All right, so I can break this up into the derivative of 3x plus the derivative of 7. All right, I can pull the constant out in front of the derivative times x plus the derivative of 7. 7 is a constant, so the derivative of a constant, go back up at the top, is 0. The derivative of x, all right, back up here again, the derivative of just x is 1 times 3. So we end up with 3, which isn't too surprising because this is the line 3x plus 7. Everywhere on that line has a slope of 3. So the derivative anywhere, the slope of the tangent line anywhere on that line is always going to be 3. All right, so let's try another one here. Let's do a negative 8x plus pi plus e. So if I break this up, negative 8x plus the derivative of pi plus the derivative of e. All right. Again, we're going to find that there are shortcuts to this, but I'm going through all of the steps here. The derivative of negative 8x, I can pull the negative 8 in front. The derivative of pi is a constant. The derivative of a constant is 0. Derivative of e is also a constant. Remember, that's like 2.71, so on. Just like pi is about 3.14 or so on. So e is a constant. The derivative of it is going to be 0. Here, the derivative of x with respect to x is just 1. And we still have a negative 8 in front. Plus a bunch of zeros gives me negative 8 as your final answer. All right. On the next page, we've got something called the power rule. And the power rule allows me to take the derivative of this, and we're not going to go through exactly the proof of this, but the power rule states that I can pull the power down in front and decrease by 1. And we saw a little bit of this earlier and even on those previous examples. So for example, the derivative of x squared is pull the power down in front, decrease by 1, or 2x. Right. So we can do this by finding the derivative of f of x if f of x is equal to x squared by using our limit definition. Limit as h approaches 0 of f of x plus h. So put the x plus h in for f of x, square it, minus f of x divided by h. Limit as h approaches 0 of, FOIL this out, x squared plus 2xh plus h squared minus x squared divided by h. Remember, stuff on top should cancel, factor out the h. And I've got a 2x plus h. So if I let h go to 0, my answer is 5 minutes later, 2x. Or I could do the power rule and get 2x that way. So with that in mind, if I take the derivative of, 5x cubed, by the power rule, I pull the 3 down in front, multiply it times the 5 that's already there, and come up with 15x squared. My alternative way would be to do the limit definition. And you can see how much fun that's going to be. F prime of x equals limit as h approaches 0 of. So if I have 5, put in the x plus h, cube it, right, minus 5x cubed, all divided by h. I would have to multiply that out 3 times, take an x plus h times an x plus h times an x plus h, then times it by 5, subtract the 5x cubed, cancel or factor out the h and cancel the h, and then sub an h as 0 in for all the other h's, and eventually get 15x squared, which that would probably take more than 5 minutes to do. So the power rule comes in really handy here. So one of the things that you'll want to note is when you're using the power rule, the variables need to be up in the numerator. So if they're not, you need to move them up. How do we move them up? For example, if it's 1 over x cubed, I can move it up to the numerator and make it x to the negative 3. Once it's up in a numerator, then I can go ahead and use the power rule. The other thing is to rewrite radicals as fractional exponents. So again, a power rule requires powers, not radicals. So if I have, for example, the cube root of x squared, and I want to take the derivative of that, the first thing I want to do is rewrite it as a power before I take a derivative. All right, so a couple of things there to keep in mind when I do this next example. Find the derivative of the following function. Again, this would be a hot mess if I had to do the limit definition. Everywhere there's an x, I'd be putting in an x plus h. I'd have to FOIL and multiply everything out. It would be very, very ugly. But if I use my power rule, not so bad. Notice everything, all my variables are up in a numerator, and I don't have any radicals in the problem. So I'm going to go ahead and do calculus. Go ahead and do the power rule. Pull the power down in front, multiply it times the negative 5, and decrease the power by 1. Pull the power down in front, decrease by 1. Pull the power down in front, and decrease by 1. Pull the power down in front. Now these powers are coming down in front of a variable now, so we can use the power rule. So 2 pi, pi is just a number, x to the 1, and then the derivative of x is just 1. Now, you can pull the power down in front. Negative 11 times 1 is negative 11. X to the 0, but x to the 0 is 1. And then the derivative of a constant, and I don't care what you do to the constant cubed is still a constant, is going to be 0. This is a constant, not a variable, which means I don't get to pull the 3 down in front and call it 3e squared. E is a number, not a variable. So to finish this, it'd be negative 30 x to the 5th minus 4x cubed plus 63x squared plus 2 pi x minus 11. Let's try one more on this page. We want to find g prime of 1. So we're going to find g prime of x first and then substitute in the number 1 into our derivative. But before we find our derivative, we're going to rewrite our function. So this is still g of x. We're doing algebra here. I'm going to rewrite the square root of x as x to the 1 over 2 power. This is the square root. Rewrite power over root. X to the 5th in the denominator is going to move up. So that becomes 2x to the negative 5. This is minus 6x to the 2/3. I'm going to leave the square root of 21 alone because 21 is a constant. And when I take the derivative of it, it's eventually going to go to 0. And the same with the number 8. It's a constant. Now go ahead and take the derivative. Pull the power down in front. So 1/2 times 6. And decrease by 1. So 1/2 minus 1. I'm going to write that in and we'll fix it in a minute. Pull the power down in front, multiply, and then decrease by 1. So again, subtract 1 from it. Pull the power down in front. So 6 times negative 2/3 is 4. and then decrease the power by 1. Square root of 21 is a constant. 8 is a constant. Both of those go to 0. All right, and now clean up your powers. And if you're not great with your fractions, then get great with your calculator and leave it as a fraction. So if I take, and again, if you can do it in your head, that's great. If not, write it down. If I take 1/2 minus 1 and then convert it back by doing math, enter, enter, I get the fraction -1/2. All right, and then I've got a minus 10x to the minus 6 and a minus 4. And again, you can take 2/3 minus 1, and that's going to be to the -1/3 power, and then a bunch of zeros. That's g prime of x. If I want g prime of 1, what's the slope of the tangent line at x equals 1? I shove in the number 1, right, and then go ahead and shove in the number 1. Use your calculator if you need to, but 1 to any power is just 1. So this is just going to be 3 minus 10 minus 4, or -11.